Hey guys, welcome to 2016 Level 2 Waves exam walkthrough. So we're going to get straight into it. So Sarah placed the candle in front of a concave mirror. Draw two rays from the candle object to locate the position of the image. Draw and label the image. Right, so basically I think the easiest two rays to do is one traveling perpendicular to the horizontal axis, so horizontal perpendicular. So that's ray number one, and that's going to reflect back downwards through the focal point. So it's going to reflect back downwards through the focal point. So that's our ray number one. Our ray number two, okay, I find it easiest the ray that goes through the point 0, 0, so it cuts at the place that the vertical or horizontal axes meet each other. So it's going to hit there. And it's going to reflect back. It's going to follow follow the law of reflection, and it's going to reflect back at the same angle theta. So basically, how are you going to ensure that it's the same angle theta? So we're going to measure how long the object is. Okay, how long is this object? And then we're going to make sure that the reflected ray passes through that exact same height but inverted. Okay, so we're just going to measure out this length. That's our length, and that's where we want our ray to pass through, right here. Alright. So now we're gonna find where the two rays intersect, and that's where our image will be formed. Oh, I think that's a bit too much now. Okay. So as you can see, the ray will be formed at where the two rays intersect, which is right where they intersect, should be right there. So that's where our image is. Not quite there actually. I'm stupid. It's right here actually. All right, that's where our image will be formed. Okay, our image is it's enlarged, it's inverted, and it's real, and that's our image. And drawing the correct ray diagram there will get you an achieved. Alright, B. The candle, which has a height of 20 centimeters, is placed 140 centimeters in front of the concave mirror. The mirror has a fixed focal length of 80 centimeters. Calculate the height of the image formed. So what we're trying to find here is the HI. It gives us the HO, the candle object height, and it gives us the 140 centimeters in front of the concave mirror. So DO is given to us. It's a concave mirror, so therefore the focal length is regarded as positive, okay? So trying to find the height of the image, okay? So therefore, we're going to use the equation HI over HO equals to DI over DO, okay? So HI we don't know. No, we cannot do this right just yet. It says it has a fixed focal length of 80 centimeters. I missed that one. So we regard the focal length as positive in this case, because it's a concave mirror. And the image is formed in front of the mirror. So 1 over F is equal to 1 over DO plus 1 over DI. Focal length is 80, so 1 over 80 equals to 1 over DO, which is 140, plus 1 over DI. 1 over 80 minus 1 over 140, and you find this whole thing divided by the inverse of the entire thing, so 1 divided by that. So if we get our good calculator out, we get 1 over 80 minus. Should get us our DI should be 186.67 centimeters. That should be what our DI comes out to be. Now we're going to use that DI over DO equals to HI over HO. Our HI we don't know, so HI over HO, which is 20, is equal to DI, we found out is 186.67 over our DO, which is 140. Now we're going to cross multiply, so 20 times of 186.67 equals to 140 HI. If you solve for HI, okay, solving for HI should give you calculator. 26.66, so HI equals to 26.67 centimeters. That's your HI, and getting a correct HI there will get you a merit grade. To get an achieved grade, okay, you're finding the correct DI. So DI correct will get you an achieved. Sarah then puts the same 20 centimeter tall candle at the same 140 centimeter distance in front of a convex mirror, which also has a focal length of 80 centimeters. The images formed by the concave and convex mirrors are different. Describe two differences in the images formed and explain why these differences occur. Alright, so in the concave mirror, the image formed is it's real. Well, it depends on where it is, but it's what I'm trying to say is that the image, well, when she put it in front of the convex concave mirror, the image formed was real, inverted, and magnified. However, with the convex mirror, okay, it will always be a virtual image, and it will always be upright. And it will always be diminished. Okay, so concave mirror produces the magnified, real, and inverted image. While convex mirror produces virtual, diminished, and upright image. And so to get a merit grade, two aspects of both. Yeah, so that should get you a merit grade. That's two types. That's two aspects described, and achieved is basically just one aspect. Basically, one aspect is achieved. The same 20 centimeter tall candle is again placed in front of the first concave mirror of focal length 80 centimeters. The candle is moved until the image is upright and is 3 times the size of the object. Describe the nature of the image. Okay, so the same as a concave mirror. So image is upright and 3 times the size. So the nature of the image, okay, is because it's upright, okay, the upright image, therefore the image must be a virtual image. Virtual images are always upright. Calculate the distance the candle. Hey guys, welcome back. So I had the video got cut off. The screen recorder decided to just shut off for no reason at all. So I have to redo quite a lot, but it's okay. I'm gonna get straight back to where it cut off. So the same 20 centimeter tall candle is again placed in front of the first concave mirror of focal length 80 centimeters. The candle is moved until the image is upright and is 3 times the size of the object. Okay, so calculate the distance of the candle object is away from the mirror. So the distance of the candle object is away from the mirror. That's basically the DO we want to find. We have our 20 centimeter tall candle, so our H, height of the object, is 20 centimeters. Our focal length is 80 centimeters. And the image is upright, so it's virtual, and it's 3 times the size of the object, so magnification equals to 3. And we need to find our DO. So in this question, we actually don't have a lot of information, so we're going to have to be using our substitution or simultaneous equations in order to find what our DO is. So you need to use both the HI over HO and 1 over F equals to 1 over DO plus 1 over DI equations, and put them together in order to find your DO. So you can say that 1 over F equals to 1 over DO plus 1 over DI. However, notice that this is a concave mirror. And if it's a concave mirror, then you actually have a negative focal length, and you also have the negative distance image, okay? So therefore, this equation will change and will actually become 1 over negative F equals to 1 over DO plus 1 over negative di. So why is it negative di? The reason it's negative di is because the image is formed behind the mirror. That's the one thing you need to keep in mind. It's formed behind the mirror. So therefore, your di is also negative. So now you have your formula. So f equals to 80. So 1 over negative 80 equals to 1 over do, which we're trying to find, plus, well, technically, the negative di makes it minus 1 over di. Alright, so now we're going to use our high over ho and our magnification relationship. So we can say hi over ho equals to di over do, which equals to 3. Our magnification is 3. So you can say that 3 do equals to di. You move the do to the other side, so 3 do equals to di. So now you can substitute the 3 over do into the di in this formula. Okay? So then I can say 1 over negative 80 is equal to 1 over do, which we still don't know. Minus 1 over 3 do. 1 over negative 80 equals to 3 over 3 do. Okay, we want to make the two denominators the same. If the two denominators are the same, we can subtract or multiply or do whatever we need to do to the numerator. Okay, so now it'll just become negative 1 over 80 is equal to 2 over 3 do. And now our final step is just to cross multiply. Okay, that's cross multiply. So 100 and I'll come back to the bottom. So I'll say 160 is equal to negative 3 do. So therefore we move the negative 3 to the other side, and you should get 160 divided by negative 3 should get your answer as negative 53.33 centimeters. But the negative 53.33 centimeters is basically just means 53.33 centimeters behind the, counting from the back of the mirror. The negative just represents the change in as in a direction, you know what I mean? As in if it's in front or behind the mirror. So that only determines behind or front, okay? So it's best to not leave your answer as a negative, okay? That's not really efficient. So you can say the answer comes out to negative 53.33, but you can say that this means image is this means that image is 53.33 centimeters behind the mirror. And that is the best way to leave your final answer, okay? Just make sure you make that final statement to make the marker understand that you understand what the negative actually means, okay? Because it's impossible to have the actual negative distance in the real life, okay? The only reason is just once again in physics, mainly to represent the change in direction, okay? So don't let that actually confuse you. Alright, so I'm going to move on to question 2. Refraction and lenses. Okay, so in this question we're going to be looking at refraction. Basically what the question says, refraction and lenses. Sorry, the last question, that was the excellence question. That was the excellence question. So to get a merit grade, you're looking at the idea. So if you write it, if you're basically understanding that it has a negative focal length and a negative distance image, and understanding that the magnification equals to 3. So basically just understanding the information is enough to get you a merit. To get an achieved, all we have to say is just the image is virtual. Achieved. Now we have refraction and lenses. Sarah had found 2 pairs of old reading glasses in her grandmother's drawer. One pair was quite heavy and was made out of glass lenses, and the other pair was quite light, made out of plastic lenses. Sarah has learned from her physics class, good job, that glass and plastic have different refractive indexes. To investigate further, she places a transparent glass and transparent plastic rectangular block together and shines a grain laser beam as shown below. Show that the refractive index for plastic is 1.43. Once again, we're going to be using the Snell's law in order to find the relationships, okay? So you know that n1 sine theta 1 equals to n2 sine theta 2. Our ray is moving from glass to plastic, so our n1 will be the glass, now n2 will be the plastic. So n1 is 1.55. Our theta is 40 degrees, and n2 we don't know, and sine of 44 degrees. So now, once again, we just need to do some calculator work, okay? So remember to set your calculator to degrees. If you don't set your calculator to degrees, you'll probably get a negative answer, and nobody likes that. So divided by sine 44. You should get your answer as 1.43. I'm just checking. Yeah, you get your answer as 1.43. Well, technically it's a bit more than 1.43, but it rounds down to 1.43, so you can just say it's 1.43. This question is a achieved question, and that's achieved only. Alright, next question. If the angle of incidence in the glass becomes greater than the critical angle, then the light is totally internally reflected and no refraction takes place. Calculate the critical angle for the glass-plastic boundary to 3 significant figures, okay? Alright, the critical angle means that the angle of refraction is 90 degrees. And the corresponding angle of incidence is critical angle. So now that you now that you know both of the refractive indexes, so you know that plastic is 1.43 and glass is 1.55, and you're just substituting these numbers in. So you can say, once again, Snell's law, n1 sine 1 equals to n2 sine theta 2. Our n1, okay, once again, it's a glass-plastic boundary, so n1 will be the glass. So 1.55 sine theta 1 we're trying to find, that's the angle of incidence we're trying to find. And that equals to n2, which is 1.43, sine 90. It's sine 90 because there's a critical angle, so the refraction is 90 degrees perpendicular to the normal. Alright, so now just calculator work here. That's all we need to do. So basically, if we simplify this, sine 90, that equals to 1. So therefore, all you're doing is 1.43 divided by 1.55 and sine inverse of that. That should give you your theta 1. So theta 1, okay, if you do the calculated work, you should get that your answer is 67.3 degrees. 67.3 degrees, and that'll get you a merit grade. To get an achieved grade, okay, you're looking at correct formula and correct substitution. So getting up to this part here, it's achieved. Alright, this diagram below shows a simplified version of the glass lens used in the reading glasses. Draw a ray diagram to find the positions of both focal points. Label a focal point on the diagram below. Alright, so for this question, okay, we're going to be using a rule that says when the ray passes through the focal point, then it will refract 90 degrees or parallel to the horizontal axis, okay? So as you can see, if we have the image here, if we dot this back, that's where our refracted ray would refract once it passes through the focal point. So our ray must pass through this point. So therefore our ray will pass directly to that point through the focal point and refract parallel to the parallel to the horizontal axis, and therefore it's going to refract, and therefore it's going to head towards the image. So the point that cuts the horizontal axis is where our focal point is. So our focal point will actually be here. Our focal point is same on both ways, okay, but you can also use another rule. Okay, another rule is saying that if the ray passes parallel to the horizontal axis, then it will pass through the focal point to the image. So that's how you find your second focal point, by using a rule. But you know that both sides the focal point is the same, so it should look something like this. Alright, so once again, our focal point will be here. So really state the focal length. So 1 square is 0.5, 3 times 0.5, that equals to 1.5 centimeters. And that will actually get you a merit grade, okay? So that's an easy merit there. To get an achieved grade, you're looking for 1 correct ray only. So you actually do need to draw 2 correct rays, okay? So just make sure, you did need to draw 2 correct rays. You couldn't just label one side and assume it's the same on the other side, which it is, but NCEA is sometimes a bit strict, I should say. I'm not going to talk badly about NCEA, but NCEA can be a bit strict sometimes, so just make sure that you try to, I don't know, I'm not sure, just be careful out there, I must say. The above diagram shows an inverted diminished image. By modifying the properties of the lens or its position, it is possible to create an image that's enlarged and upright. Explain 3 different changes that could allow this to happen. So basically, it has to be within the focal point in order for it to create the enlarged and upright. So to create the virtual image with the lens, that's the convex lens, you need to create the virtual image. So that's the one that the virtual rays extend backwards. The only way to do that, in this case, is if the object is inside the focal point. You can do this by either moving the object closer, so that it's inside the focal point, or you can move the mirror closer to the object so that the focal point is inside, so that the object is now inside the focal point. So basically, just trying to find ways to increase the focal point, to move the object inside the focal point. So your opening statement could be, in order for the the upright enlarged image to be produced. In order for it to be produced, we need to position the image inside the F, okay? So basically, we can move. So basically, number one, we could move the object closer to the to the lens, or the lens closer to the object. Okay, so that's one way of doing it. So the other way we can do it is by increasing our focal point. So a way to increase our focal point is to change the refractive index of our glass. So we want the glass to refract less so that the ray, so for example, we have this ray right now, right? So for example, we change the refractive index so that the focal point refracts differently. So it might refract here now. So in order to do that, okay, we need to actually we need to could be increase or decrease. Just let me think. So if it's it's pretty complicated. So I need to use Newton's law here. So if we increase sin theta 2, that stays the same. So that divided by a larger number will give us a lower that. So give us lower angle of refraction. Sorry, is this sine of a low number? Should be sine of a small. Alright, okay, so sine of a smaller number does give you a small result, so I'm sorry guys, just hold up. Let me think this through. If it's N2, decrease. So this whole thing will decrease. So this will decrease. So our angle of refraction will decrease. If we decrease the refractor, if we decrease this refractor, so I just skip ahead in the video, sorry guys, apologize for this. So if we decrease the refractive index, then this will increase, and this will increase. Oh no, it's going from glass to air. So if we, sorry guys, I'm thinking this the wrong way this entire time. So we're going from glass to air. So that's gonna stay the same. If we into glass to air. So if we increase the N1, then this will become higher. So this will become higher. Yeah, okay, so I got it now. So another way we can do it is by decreasing the refractive index of the lens. Okay, the reason for this is when the ray comes out of the lens, it will be moving from glass to air. Okay, so now we have our Snooks law, N1 sine theta 1 equals to N2 sine theta 2. So our N1 is the glass, now N2 is air. We can't change the refractive index of air, okay, but we can change our lens, okay? So if we change our N1, if we make our N1 lower, then this whole result will become lower. So therefore, when we move the N2 across, it will be a lower number divided by the same number. So this will generate a lower result. If we generate a lower result here, then therefore sine theta 2, so the theta 2 will also drop. If we have a lower angle of refraction, it will stay above the angle of, it will stay above the horizontal axis for longer, so therefore our focal length will increase. So all we have to say here, we can say we could decrease the refractive index of our lens to cause a lower angle of refraction, meaning that the focal length will increase to potentially be for the object to be inside the F. So one more way we could change the focal length, we could change the center of curvature. So if we decrease the center of curvature, then if we decrease the curvature, then the focal length will also decrease. But if we increase the center of curvature, then the focal point will increase. So we're looking for a way to increase increase the center of curvature. The one way we can do that is by making making it less curved. If we make it less curved, then it'll take longer for it to make a full circle. And if it takes longer to make a full circle, then our radius will be further along the axis. So therefore, our center of curvature will increase. If our center of curvature increases, then our focal length will increase with it. So therefore, it could be potentially the object could be potentially inside the focal length after the change. So if we like it, just making a less curved lens basically. So one with a larger radius of curvature. So basically, we could also make our lens less curved, so that the center of curvature increases. So if the center of curvature increases, then the F will also increase, so that the object could be inside the F. Yeah, it's a pretty. I must say so myself. This is a pretty tough question in my opinion. There's a lot of things there that's pretty high level. Especially looking at the Schnell's law with the increasing or decreasing the refractive index. That was especially pretty tough. You have to think about the ray going from the glass into the air, and as a result, if you decreased or increased the n1, what will happen to the sine theta 2? So basically, what effect does one variable have on the theta 2? And that was actually pretty difficult in my opinion. Yeah, so that's a pretty tough question. Okay, it is an excellence question, but it was pretty tough. Again, excellence question for all 3 points. To get a merit question, you're basically having 2 correct points, and to get an achieve, you're looking for either one, basically 1 out of 3. So 1 out of 3 is just an achieved. Yeah, so it's pretty difficult excellence question in my opinion, but it's nothing that we haven't learned in my opinion. We did have learned most of these things. So just when it comes to the exam and you get hit with a curveball, you need to relax, okay? Because everything in the exam is just something that you've learned, but with a twist. So maybe you need to think about with a different way, basically. Just some exam tips, basically. If it gives you something unexpected, okay, it's definitely something you've learned, okay? If it's not something you've learned, then they won't put it in the test, okay? Or they'll remove the question after the exam. So either way, that's pretty unlikely. So the likely thing is that NCAA will throw some kind of curveball at you. It will change the question up, change the wording up a little bit, maybe change the question wording, or maybe give you a question that hasn't occurred frequently in past year exam paper. Just like common curveballs, and don't panic, okay? Just think about other ways that you can solve the question, okay? And yeah, that's if I'll cover question 3 in a separate video. It is getting quite late today, so I have to cut it off here. Hope you enjoyed this video, and sorry about the last question where I had to take a long time. That was pretty tough question, so apologize for that. But other than that, thank you for watching this video, and I hope you enjoyed, and I'll see you all in the next one. Thank you. Bye.